Pleasant day to our panelists, to our advisors, and to whole faculty and staff. So, for the research defense, we'll be starting with the very root cause of the problem, which is the COVID-19 global pandemic outbreak. So, COVID caused a lot of lives, which expose how poor our healthcare system is in different countries worldwide, and which had a great impact and the greatest cause of the economic recession we've experienced for the past years. So, with this in mind, the greatest question is that what can we do to prevent a virus transmission? Of course, basically, through micro steps and simple ways, what we can do to contribute significantly as individuals. They say that prevention is better than cure. And with that, we believe that hand hygiene is the most basic but the most powerful weapon that we can use to contribute to giving a stop to this pandemic that we are experiencing nowadays. That's why the research proponents, and namely
Jose Alvaro II,
yours truly, Casabana Rica Mayes,
Fabian Jimulayan,
and Angel Hapin.
with our research instructor, Engineer Jose Rizaldi de Armas, and our research advisor, Engineer Earl Jason Alvaran, is presenting our paper to the Faculty of Engineering of Electronics Engineering of the De La Salle University Das Marinas. And we came up with the thesis entitled Arduino Microcontroller System-Based Hand Disinfection Automation Machine to serve as our contribution as electronics engineering students to the current problem that we have these trying times of the pandemic. So what's the background of the study? So disinfecting of hands is not only through the use of water and soap, but it can also be done with the help of an automated hand disinfection machine, like this that we'll be showing on the screen. What's the problem with our existing system? The problem is that, according to Centers for Disease Control and Prevention, an individual should put enough sanitizer to cover all surfaces. But the problem is that many hand disinfection processes and procedures that we have nowadays just deliver insufficient amount of hand disinfection solution to our hands. And that's the real problem here and the question that we are trying to solve. So with that, another problem is that automation is not maximized. Living in a technological world, we should maximize automation as engineers. And the problem is that hand disinfection currently involves an interaction with our security personals, which adds up to the possible contact imposing risk of virus and germs transmission. So with that, the researchers came up with the objectives and the primary goals of the study, which are first, to focus on constructing a working circuit that automates hand disinfection by detecting the user hands inside the machine through sensors. Second is to optimize the hand detection process by setting the good location of the nozzles as well as the good number and placement of the sensors for maximum hand disinfection coverage. And third one is to create a hand disinfection with an enclosure for the disinfection process. Now, for the scope of the study, Jose?
So, in our scope of the study, we will be focusing on creating a microcontroller-based hand disinfection machine, so specifically Arduino Nano. Then, a home-based setup will be performed to conduct tests at Barangay Zone 1, Dasmariñas, Cavite. Then, typical use of hand disinfection machine is for the public, but hand hygiene should also be practiced at home. So the machine is for hand disinfection, but it is also limited to guarantee the killing of the virus, which is not part of the research. The disinfectant solution used for the machine will be the one responsible in killing the germs and viruses. So let's move on to the limitations of the study. Pandemic crisis while doing the research pose as a problem. Travel restrictions and home quarantine limits the mobility of researchers to obtain the components. Different hand sizes of users for testing are part of the limitation of the study that may affect the performance of the machine. Another limitation is the unconventional formation of hands. These formations can be fingers crossed, closed fist, fingers together, normally open, and amputated. Thus, it may affect the performance of the machine.
Now, for the chapter 3, or our methodology that the researchers used to came up and to perform the research. First is that the researchers gather supporting sources and researchers through our chapter 2 or related literature to come up with the information significant for the completion of the research. Next is that the development of system process and architecture to better understand how the system works and how could the system be better and be optimized in terms of its performance. Now, in terms of our system block diagram, the researchers use this to relay the information to people to better understand how our prototype system works through the blockings of the components and how the signals will go through and go out of our system. Now, for the hardware components,
So for the hardware components, we use a Arduino Nano microcontroller wherein we program to make the IR sensors be responsive once the user insert their hands. So here is the list of our components. Arduino Nano microcontroller, IR proximity sensors, LCD display, DC water pump, universal printed circuit board or known as PCB, resistors, relay module, capacitors, LED indicators, power module, and also connecting wires. So here is our prototype hardware casing materials. So we have a 3D SketchUp system design. So the design is composed of screws and bolts, ladding, GI sheet for casing walls, aluminum tubular for borders, piping and tubes, sprinkle nozzles, water tank container, and supporting frame.
for the code and programming logic,
So in terms of the code and the programming logic, here is the flowchart on the left, which indicates the flow of the program installed in the microcontroller. So the microcontroller will declare or have use the sensors as the input for the program. Then it will run through a decision if the sensors have been activated, and if all sensors are activated, it will release disinfectant for a few seconds indicated in the program, and the program will end. If not all sensors are active, then it will still release disinfectant, but it will release for a shorter period of time, and the program will end. If these two conditions are not satisfied, it will loop again until the machine detects that there are sensors that has been active. So on the upper right, it is the code used to initialize the internal timer of the microcontroller in the Arduino Nano, which is the Atmega 328. And on the other side, or the lower right, is the XOR gate, which is the one of the logic heavily used in able to achieve the program used in the flowchart. So for the next slide, this is the sample screenshot of the source code on the left, and on the right side is the time or the duration time used in our program. So for two IR sensors, the maximum duration time is 6 seconds. If one IR sensor is activated, it will run about 3 seconds. For the three IR proximity sensors, the maximum duration time is 9 seconds, and the minimum duration time is about 3 seconds.
Now, for our circuit schematic and PCB design. So here is a circuit schematic for our two IR sensors, showing how the IR sensors were connected to the digital pins of the Arduino, how the 5 volts from our regulated power supply is connected to the VN of the Arduino Nano, and then we isolated a 5 volts voltage supply to supply regulated 5 volts to our relay module to maintain the needed requirement of the DC motor water pump. So LCD is also connected to our Arduino, so we can have an display for the users view, so they can know if they already spread their hands or they need to spread it more. So we have here the PCB design that we use a true hole printed circuit board, a universal printed circuit board, to solder all of the components to have a continuity of the connection. And then for our 3-IR proximity sensors, the connection will be the same with the 2-IR sensors. The only difference will be we use 3-IR sensors and 3 digital pins of the Arduino Nano is used. And this is our universal printed circuit board layout for the 3 sensors. And then for our 4-IR proximity sensors, the connection will be the same with the 2 and 3-IR sensors. The only difference is that we'll be adding another one, a total of 4-IR sensors. And the PCB will look like this with the 4 sensors covering the whole surface of the PCB like a rectangle layout. Then for our machine prototype sketch, we have here our research from our supporting sources, wherein we elaborated the average length and width or breadth of our hands from both the male and the female gender category to know what is the average sizes of hands, which we use as our basis to design our prototype sketches. So this is the top view of our prototype sketch, our side view with the front view, and then our side view as well. For the final and improved design, we have here Jose Alvaro.
So we have here flashed on a screen is the prototype model, which showcases the foundation and materials used for this casing. So as we can see here, we have in this front view the 2 holes in which our hands will be inserted, and the container inside the prototype, which will be the container for our disinfectant. Then we also have here the top view of our prototype. We will have here the LCD or the display, then the sensor locations. So for the side view, here is the snip of the model. Then the rear view as well.
Now, to explain and to better understand how the system works, we'll be having this circuit diagram here. So let's have the process one by one, how the system works. First one, the power module supplies 5 volts to our IR sensors and Arduino Nano microcontroller. So the IR proximity sensors are connected to the digital pins of the program Arduino Nano. And then the next step is that IR sensors will send signals to the Arduino Nano when it is activated by detecting the user hands inside the disinfection machine. Arduino Nano will process the signal to activate the relay module. The relay module acts as a switch to activate or stop the DC motor. And then the power module supplies an isolated 5 volts to our relay module and DC pump motor. So the capacitor here in parallel with our isolated 5 volts voltage supply acts as a regulator of the voltage that maintains the supply of the voltage to be enough for the DC motor pump requirement. And then the LED in series with a 220 ohm resistor acts as an indicator for the system's on and off operation. And after the indicator, we'll be having the DC motor pumping disinfectant solution to both of the nozzles connected to the motor through a hose. So for our circuit test setup, Yanni.
So for our circuit test setup, this is the setup for two IR proximity sensors, which is next slide. Next slide, please. There. And we have the testing and data gathering. So with the circuit setup, it was conducted on the Ascension Village, Guevara Street, Zone 1, Dasmariñas City, Cavite. The process of testing is on the open kitchen area of the house, which showed in the pictures below.
So with that, we'll be showing the testing and data gathering procedure demonstration through a video, and we'll be showing the video in the screen. So this is the circuit test setup for the two sections of the hand disinfection machine, wherein we use a power bank as our power source for our circuit, which will power our Arduino Nano for both of the sections. We also use a power module that will output 5 volts voltage that will power our relay here, which will serve as the isolated power source for our actuator. So this relay will serve as the actuator for our IR sensors here, which are placed in accordance to the distance that we will be setting for our testing setup. So for each of the sections, we use 3 IR sensors that, based on our test setup, provides an optimized disinfection for both of the sections. And here we have our DC water pump, which motors is powered by the 5 volts from our isolated voltage source. And here are our nozzles for the two sections, which will pump water for our disinfection machines. So for our hand disinfection machine testing, when both of the user hands were inserted and activated the IR sensors, the nozzle automatically sprinkle water from the DC water pump. Initial test setup for one section is also demonstrated with the use of a timer to measure and record the response time and the operation duration of the machine. The LCD will display spread hands for best result if not all of the IR sensors has been activated. But when all of the sensors has been activated, it will display disinfecting hands, which will serve as the optimized performance of the machine. Then after that, it will display thank you from the LCD once the disinfection process is done. Data for the nozzle height is also tested to arrive at an optimized disinfection coverage. A paper was placed under the nozzles to show that the system is working and provides a maximum hand disinfection coverage. Unconventional hand formations like closed fist, fingers together, crossed fingers, and assumed to be amputated hands were also put to test to demonstrate how effective the machine is in detecting hands regardless of how it is inserted inside the machine. Actual tests with the prototype and the user hands were performed considering both male and female hands to represent different hand sizes. After the disinfection process, the disinfected hands were placed over paper to check the disinfection coverage to determine if the coverage is wide or small. That will serve as a qualitative data to characterize the performance of the machine. With the automated hands disinfection machine, everyone should do their social responsibility, disinfect their hands, prevent virus transmission, so we can all stop the pandemic. Now, for data processing and data gathering, we'll be considering the tables wherein certain parameters like the hand sizes, the sensor's distance, the number of proximity sensors, the placement of the sensors, and the layout of the IR sensors are all considered in the tabular format. So we'll be using the tables to gather quantitative and qualitative data to characterize the performance of the machine and to characterize how the machine covers the entire hands in terms of its disinfection coverage. So the length, the width of the hands are also considered, are also recorded and measured. The nozzle height is also measured and recorded, as well as the uncontrolled parameters, which are all qualitative that will determine how effective the machine, regardless of how the hands were inserted inside of it. Then for our chapter 4 and results and discussion, let's have the first table. Interpreting the first table we have here, our general uh, analysis that as the IR sensor's distance decreases and gets nearer at the reference center point, which is our nozzle location, the operation duration time increases, which means that all sensors are activated and are in active phase, and the disinfection coverage is at its maximum. As you can see on our graph here, uh, on our IR sensor distance versus operation time, as our IR sensor distance increases, the performance of the machine decreases significantly. So it is recommendable to maintain a near distance of our IR sensors. Then for the next one,
For the next one, as we can see, the graph is at is around 6 seconds. It means that the longer the operation duration time, the wider the hand coverage. As we see on the table, the highest, the more hand coverage area is on the trial 3, which has a 6.05 seconds. And as seen on the graph, it has also the highest uh, hand coverage. And also in terms of response time, it will deter in terms of response time, the machine operates effectively since it is less than the response is less than a second. For the next slide, the sensor locations is varied, but the hand size are inconstant. So as we can see on the data, the farther the distance, the less duration time it covers. Next slide. So with that, we can see that in our graph, as we can see, as the length increases, the duration time decreases.
so it is advisable that the distance should be minimized with respect to the reference point, if I may add to that. So let's have the next one.
As and for and this and the next one is the measured width. So as we can see, it is the same. So if the distance is farther, the duration time will also decrease.
So basically, the optimist performance of the machine will be based on the sensor's distance from the reference point and in accordance to the sizes of the hands. So let's have the next analysis.
So now let's proceed to our 3IR sensor, wherein we vary the sensor distance. So the user that we have here is a adult male with a constant hand size of 7 inches width and 7.5 inches in length. So we also have here a constant nozzle height, which is the 4 inches here. So as you can see in the um, line graph, the x-axis that we have here is the sensor location, which is the length, and we measure the length in inches. And we have here the y-axis, which is the operation time. Here is the duration and response time of the system. So we can see here the correlation of the 3IR sensor versus its operation time with constant male hand size. So now let's proceed to our next slide. So in continuation from the previous slide, here is the table and line graph. So it's just the same in the previous slide, but the perimeter that we use here is the width measurement, this distance, as we can see here in the x-axis of the line graph. And so the distance of the width measurement is from the IR sensor, which the microcontroller, I mean, which is the center reference point. And here in the line graph, we can see that the y-axis is also the same, which is the operation time and measured in seconds. So the analysis that we have here in this part is that as the IR sensor gets close to each other or decreases, the duration time of the system increases, which means that all the IR sensor are hit by the user or in active phase.
Now for the next analysis, let's have Jose.
So we have here for the next test analysis, the researchers consider the varying hand size of the user. So this test setup doesn't consider the gender of the user with a constant nozzle height of 4 inches. So in here in the table, we can see the test results of the testing setup. So we have here the varying hand size and width and length of the hand. Then we have here the sensor location as well. So the sensor location is constant. Then we have here the line graph of the length versus operation time. So in this part of the test analysis, we determine the sensor distance versus operation time. So with varying hand size category. Then in here, as we can see here that we have separated the parameters for the length of the hand and the width of the hand. So for the length, we have here the range of percent error is from 0.11, which is the lowest, then up to the highest or the maximum, which is the 5.44 percentage error. Then we have here for the width, which has the lowest also 0.11, then the highest is 5.44% of percent error. So the analysis in here is that as the sensor may be closer with each other, the more the operation time will be more fully effective. So the duration and the response time will be the operation time. So the operation time will be at its maximum if the sensor or all of the sensors will be hit at each other. So if all of the sensors are being hit, so the more the operation time will be.
And
So
as,
next one.
and as you can see from our qualitative data for the hand coverage, the hands are fully covered with the disinfectant solution. So this means that this is the optimized location of the IR sensors. So let's have the next slide.
So in here, we have here the three IR sensors with varying hand sizes as well. So the only thing changed is the setup of the sensor location, which is in parallel. So we have here the table of the test results with different sensor location, but the size or the length and the width of the hands will be varying. So as we can see here in the percent error, we have here for the length, the smallest percentage will be 0.22 up to 0.67. So for the width, we have the same percent error as well. So the conclusion for this one, for this test setup is that 3IR sensors layout delivers the most optimized disinfection coverage with the smallest percent difference from the expected actual result. So the 3IR sensors um, thus have the most or the optimized position or location of the sensor.
So like have the next slide. So for the next slide, Jose.
Then in here as well, we can see here that we use three IR sensors, but we have here the varying nozzle height for adult male constant hand sizes. So in here, we have here the um, constant location for the sensors, but the only thing that varies is the height of the nozzle. So we have here the male hand size, which is constant. Then we proceed to the table for the percent error. So as we can see here that we have here the lowest percent error, which is 0.11. Then the highest is 1.3. So we can conclude here that we have the highest or we have the most duration time in here at the 4 inches height, which is 9.12 inches. And we have the lowest duration time, which is 8.96 for the height of 3 inches. Then we can see here that the highest response time is 0.47 for the 4 inches of the height. So we have here the conclusion that the best nozzle height would be 4 inches as it will have the most maximum duration of 9.12 or the highest. So that's it for this part of testing.
So let's have the next testing for the 4IR sensors, Gel. So for the
So
4IR
for
sensor,
the 4
yeah.
IR sensor, we can see here the trend of the correlated of the 4 IR sensor distance versus its operation time. So in this part, we are now varying the sensor location. So next, we can see in the table the accuracy of the system by looking at the percentage error. So in here we have 0.3, 0.83 rather, percentage error with the length of 1.5 inches in sensor. So we can say here as the sensor comes closer to each other, it is more optimized.
And as the sensors go farther from from the reference point, it greatly affects the performance of the machine. It decreases the efficiency of the machine. And as you can see, since the 4-IR sensors deliver a great, a higher percent difference, which is 5.83%, um, 3-IR sensors is considered for the general testing setup for the optimized disinfection process. So let's have the next one, which is the uncontrolled parameters. Yani.
So for the uncontrolled parameters, as we can see, the highest percent error in this test is 4.33, and for the lowest percent error is about 1.6. As we can see, there are different forms of hand formation, but on the duration time does not reach its maximum duration time, which is 9 seconds, since it uses 3 sensors. And as we can see that as the if the user does not spread their hands or spread their spread their hands, it will not reach its maximum duration time. Thus, it does not reach the maximum hand coverage for the hand disinfection machine, and the machine will respond to spread their hands to achieve its optimum result.
So, generally speaking, the researchers wanted to point out that at the very start, the limitation of the project or of the machine will be the unconventional formation of hands, wherein when the user inserted their hands closed fist and they weren't able to hit the IR sensors, um, the performance will be decreased, but it can still function. So that's one of the limitations of the machine. So with all of the data that we've gathered through our processes and through our procedures, we'll be now proceeding with our chapter 5 or with our conclusions and recommendations. So overall, with all of the data that we've gathered and summarizing all of the data that the researchers, we will be answering the objectives of the study with the arrived finalized conclusions listed below. So let's have the first objective, which is to focus on constructing a working circuit that automates hand disinfection by detecting the user hands inside the machine through sensors. So answering the objectives with met the requirements of the objectives, which is we'll be having a conclusion that the researchers conclude that the hand disinfection machine is automated with a recorded quick response time ranging from 0.08 to 0.81 seconds, which is really short, which indicates that the machine can detect hands fast autonomously. So for the next conclusion, Yani.
For the next conclusion, the researchers conclude that hand disinfection machine has an optimized operation duration time for the disinfection process, which is almost close to the actual expected values or the program value to the machine, with a minimal percent difference ranging from 0.11% as the lowest and 3% as the highest, which proves the high effectiveness of the automated machine.
Next objective, the researchers wanted to optimize the hand detection process by setting the good location of the nozzles as well as the good number and placement of sensors for maximum hand disinfection coverage. So the conclusions was that it is also concluded that the most optimized location of the nozzle is at the center of the perimeter area of disinfection, and the nozzle height that provides the maximum hand disinfection coverage is 4 inches from the base of the machine's hand hole. So for the next conclusion, let's have Jill.
So it is concluded that three infrared proximity sensor for the hand disinfection machine delivers the most efficient hand detection response and disinfection coverage results.
Now, from these conclusions, we'll be having our finalized height of the nozzles from our hole, considering our prototype measurement and the casing size. So that's gonna be our two nozzles will be 4 inches from the top to the hole of our casing. So for our next objective, Joe.
So for the next objective we have here is to optimize the hand detection process by setting the good location of the nozzles as well as the good number and placement of sensors for maximum hand disinfection coverage.
So
So for the conclusion, we have here it was concluded that the most advisable placement of the infrared proximity sensors in the hand disinfection machine for the optimized automated detection of the hands is a triangular shaped layout with respect to the set perimeter area of the disinfection coverage.
so
So we
next.
have here
Mhm.
the figure which shows the position of the spray nozzle. So the optimized position is this one, which is 1.5 inches from the center. Then we have here another sensor which is 3 inches below. Then we have here the length which is in 2 inches away. So both sensors will be 2 inches away from the uh, each other, which makes it 4 inches away. So this position of sensors will be the most optimized based on the test results.
So for the last objective, we aim to create a hand disinfection machine with an enclosure for the disinfection process. So our conclusion will be the researchers finalized that providing an enclosure to the disinfection area of the machine contributes and ensure a maximum hand disinfection coverage. So with that, the researchers were able to meet the three objectives with all of the conclusions derive from all of the data, results, and procedures that were performed all throughout the research process. Now, from our conclusions and from our procedures, we'll be having our recommendations. After comprehensive analysis of data and conclusion, the researchers proposed the following recommendations below. So next one is to provide a timer feature display to the machine that will show the response and duration time of the system. So this will contribute to the automation factor that will make uh, a better prototype version. So next is to provide a closer distance from the user's hands and the IR proximity sensor, which will reduce the system's response time. So uh, the more closer the IR sensor is to the hands, the more fast or quick the response time will be. Then, for another recommendation, we can make use of a conveyor belt system for movable spray nozzle that will surely cover the entire hands of the user. And additionally, the researchers recommend that future researchers should consider the pressure of the hose, the pressure of the water pump through the hose to make sure that the nozzle will perform its uh, optimized water sprinkling process to our hands because that was not considered during our research process. So now with all of the research process data results conclusions and recommendations will be the researchers wanted to remind everyone that we should do our social responsibility,
Disinfect your hands.
prevent the virus transmission so we can all stop the
The pandemic.
coronavirus pandemic. So this is our group, and we thank the panelists, the faculty of the College of Engineering, Architecture, and Technology, and I hope you learned a lot from our research this day. So thank you and God bless us all. Stop.